It is time for section 9.5. I'm here on SAT day. Many of you are taking the SAT right now. I am in the hub closet. As you can see, there's a vacuum cleaner, it looks like. Looks like a decent one. And some projectors and other odds and ends, some microphone stand. All right, let's get to the pre-calc, shall we? So we've got ourselves some dot product action. You might have been like, hey, we're adding and subtracting vectors. What's going on with like multiplication? Can we do that? So the product of two vectors, we do what's called the dot product. So it's not just like straight up multiplication. So if we have a vector AI plus BJ and vector W are two vectors, and the dot product of those two would be your A sub 1 times A sub 2 plus B sub 1 times B sub 2. So the result then, if I'm just taking those numbers, multiplying the A components, the B's, right? The A's, the B's get multiplied, and then I add them together, it's just going to be, you guessed it, a scalar. In other words, we're just going to get a number. That's it, okay? I feel like this can be nice to just see. Let's just jump into an example, okay? So if I want to find my dot product of V and W down here, I'd have 2 times negative 3 plus, and then 5 times 8. So that's going to be negative 6 plus 40. That's going to equal 34. Done. Beautiful. Awesome. Now, perhaps commutative? Let's see. If we flip-flop them, I would have, let's see here, W times V. Well, I'd have negative 3 times 2, or sorry, the dot product between W and V. Negative 3 times 2 plus, and then I would have 8 times 5. I'm left with, again, negative 6 plus 40, which equals 34. We're going to write down those properties in just a sec, but yes, commutative property does apply. Okay, how about V times V? So what would I do there? Well, I would have 2 times 2, excuse me, I keep saying times, the dot product of V and V, plus 5 multiplied by 5, so I get 4 plus 25, that equals 29. Very nice. You see that multiplication sign over and over, and it's just out of habit to say multiply. All right, so the dot product of V and V is 29. Okay, a little review now. Let's find our magnitude. What's the magnitude of V? I wonder why we're doing the magnitude again. That seems a little strange, doesn't it? Oh, I do know. I do know. All right, so I'd have square root of 2 squared plus 5 squared. That gives me the square root of 4 plus 5, 25, which would equal the square root of 29. That's interesting. That is interesting there, you know? 29 and root 29, perhaps a property. We'll see. Looks like we got a yellow box down there with some awesomeness. All right, now how about the magnitude of W? Well, I would have negative 3 squared plus 8 squared. That's going to be 9 plus 64. So 9 plus 64, that's the square root of 73. Okay, it's good stuff. Good stuff. So as I said, we got some properties of the dot product. So commutative property applies. Boom. We did that one first. Distributive property. That also applies. And then the one that I was just alluding to before is that the dot product of V and V, like we did in part C, is equal to the magnitude squared. If I took the square root of 29 and I squared it, boom, I'd get 29. So that's true. And the last one here, that's the dot product of the 0 vector, and the vector V is going to always equal 0. So kind of like with like multiplication, anything times 0 is 0. Same goes with the dot product. All right. So if you need to, take a screenshot, jot them down, whatever your preferred note method is, and do that now. Now, if you're wondering, why are we using the dot product? You might wonder that a lot about math classes. Like, why am I learning this? Besides it being awesome, there is a reason. So we can actually use the dot product as a part of a formula to find the angle between two vectors. Now, we could show a proof of this, and it uses the law of cosines, but half of you haven't seen law of cosines yet. So we're going to forego that proof, and we're just going to take the dot product. We're going to use it, and I want you to jot down this formula in the yellow box. All right, this is the main part here. So the cosine of theta of some angle between two vectors is equal to the dot product of those two vectors divided by the magnitude, the product of the magnitudes of those two vectors, okay? I find it helpful oftentimes to speak a formula, and that helps me to remember the dot product of two vectors divided by the product of the magnitude of those two vectors. So let's use this to figure out our angle between the two vectors. And if you are noticing there, like, hey, what I put in for the dot product divided by the product of the magnitudes, that's not going to give me the angle. That's going to give me the cosine of the angle. I'm going to have to use some inverse trig to solve for it. And I do apologize if there's background noise right now, as I'm in the hub closet, and it's not as quiet as it usually is when you children are here. You could hear a pin drop when you children are here, but right now people are returning stuff for the SAT, and apparently it's time to chit chat outside of Mr. Allen's office, my new office. Okay, find the angle between theta. Find the angle theta between those two vectors. So let's see here. I'm going to plug in the formula. I'm just going to go straight formula with this bad boy, right? Actually, you know what? No, I'm going to draw a picture first. So if we'll do u is 2 to the right and then 4 down. So I'm looking at something like this. Okay, that's going to be u. All right, that's 2 and then down 4. And then let's see here. We'll go in a different color. We'll do, so we got 5 and then up 3. So we're looking at something like maybe this. So we got 5, 3. So the angle that I'm looking for, I'll go with, I guess green will work. This is the angle that I'm looking for there. The angle between those two vectors. A picture's nice because then you kind of see it's like, hey, like, what kind of angle should I be getting here? Okay, so I'm going to use this formula here. So I'm going to have the cosine of theta is equal to, and then the dot product of the two vectors. So I'd have 2 times 5 plus negative 4 times 3, okay, all over the product of the magnitudes. So the magnitude of u is the square root of, and it'd be 2 squared plus 4 squared. That's 4 plus 16 is, so I'll do 4 plus 16. I'll show a little bit of work. And then the magnitude of v would be 25 plus 9. Okay, we should be familiar with the magnitudes. The dot product's the new thing. Okay, so let's continue this. So I'd have 10. 10 minus 12 is negative 2. I can go with that. And then we'd have the square root of 20 and 34. I like that. Okay, so I could put those together in one square root, and then I'm going to start using the calculator. That would be 680. Yeah. So now what I'm going to do here, so we have cosine of theta, right? Now, if you remember back to your introduction to trig, when you first learned how to solve for an angle in likely honors geometry, we talked about like, hey, how do you get rid of that cosine? You can't just divide by cosine. It's not cosine times theta. It's cosine of theta, right? It's a function. So what I need to do is I need to actually take the inverse. So cosine inverse on each side, that cancels out the cosines. And now I'm left with theta equals cosine inverse of negative 2 over square root of 680. There we go. I don't even care about the radical being in the denominator or simplifying that radical or rationalizing it. All I'm looking for is an answer here, okay? And I can tell you what, this is going to be an obtuse angle because it's a negative inside of that cosine there, and cosine to be negative would be in that second quadrant. So we're going to look at an angle that's larger. Now let's plug that in. So second cosine 2 divided by, I don't have fancy math type in here, square root of 680. Close it again. Boom. I forgot my negative. Let's try that again. Cosine inverse. Negative 2 divided by square root 680. Oh, Mr. Allen, forgetting your negative 2. That was hilarious. But you know what? Honestly, it's not a bad teachable moment, right? So I was like, hey, it's a negative in my cosine inverse, and I know cosine is defined in the first and second quadrant, so it's going to be obtuse in the second, so that means I should get an obtuse angle, and I get an 85. I'm like, what the heck? I checked myself before I wrecked myself. I could have gotten, I could have figured it out from there, 180 minus 85.6-ish, because I got my reference angle. But if you plug it in like that, boom, I get my correct answer there, 94.399. Degrees. I love it. Fantastic. I just heard, I think, Mr. Ortochenko saying something about me outside there. I'm going to pause the video real quick. So I found that one pretty darn cool. When you find angles between vectors, you can find the angle of each vector and then like do the math, right, to figure it out from there. But having its own formula is pretty nice. So the dot product obviously comes in handy there right away, right? I could have done inverse tangent of each one and then figured, I don't have time for that. Ain't nobody got time for that. Again, I do apologize if it gets a little background noisy. I will try to talk as loud as I possibly can. But people are returning materials from the SAT right now. All right. But this is when I got time to get the video done. It is what it is. So determine whether vectors are parallel or orthogonal. What is orthogonal? Is that something like going to the orthodontist? I don't know, man. Actually, I do know. Let's get into it. Okay. So orthogonal, you're gonna relate into perpendicularity, okay? But if it's orthogonal, it doesn't necessarily mean that it's perpendicular. If it's perpendicular, it does mean that it's orthogonal. We're gonna get into that a little bit more. All right, so two vectors are parallel. Let's start with parallel. If the lines that contain them are parallel, okay? Basically, in other words, if the slope of that vector, if those two vectors have the same slope, they're parallel, okay? So let's determine first off if these two are parallel. Well, if I look at my the two slopes here, let's see here. I've got, if I draw a V, I'm going to the right 3 and up 2, right? So the slope is 3 over 2. If I think about it as like a line. The other one, if I look at W there, I would have 6, 4. Well, 6 over 4, that reduces down to 3 over 2. Yes, they are indeed parallel, okay? So those two are awesome and parallel. Woo! All right, so how about my next two here? Well, what if they're different directions, right? What if they're different directions here? So the first one, it's the same as the green one. Ooh, voice crack. Same as the green one. Oops, I'll go back to green. So I'm going to the right 3 and up 2, so my slope again is 3 over 2. Now for the other one, which we did in blue before, I'm going to the left 6 and down 4, so my slope is, my goodness, did I do run over rise? Oh, Mr. Allen. I need to make that, oh my goodness. I'm ashamed of myself, but I won't back down here. I'm going to leave it in there. This should have been a rise of 2, a run of 3. This was a rise of 4 and a run of 6, which simplifies to 2 over 3. They are the same slope. Over here, again, I have a rise of 2 and a run of 3. I apologize. I'm going to blame the loud noises that are distracting me. I can't. I need to take full ownership. All right. So for this one, I had a rise of -4 and a run of -6, which simplifies to 2 over 3. So they have the same slopes. They are parallel, okay? So even if they're going opposite directions, if their slopes are the same, they are parallel. Fantastic, wonderful. I think we can move on from parallel. Now on to orthogonal. So if two vectors form a right angle, theta would be pi over 2 or 90 degrees, right? In this case, the vectors are perpendicular. So if they form a right angle, they are perpendicular. Or they can be considered orthogonal. So if they're perpendicular, they are orthogonal. So if we look at our our angle between two vectors formula, and I were to say, well, cosine of 90 is 0. And if I multiply by my magnitudes, I would end up with 0 equaling the dot product, okay? So, and again, when we're finding the angle between two vectors, these are both non-zero vectors in this case, okay? Otherwise, they don't have an angle between them. So it's only if they have an angle between them. So it can't include the 0 vector, which would mean that the magnitudes would have to be some positive number, okay? So the dot product is 0, would then imply that they are orthogonal, okay? Now, the reason why we're using the word orthogonal, again, that's going to be 0. So the reason why we're using the word orthogonal is because of this. If my dot product is 0, and that dot product was calculated with a 0 vector, okay? So let's say that V is some vector. And then let's say that we have multiplied by the 0 vector. Well, that's still going to give me 0, right? The dot product between that vector and the 0 vector is going to be 0. So, but if that 0 vector has no direction, has no magnitude, we're not forming any angle, so it's not a right angle, it's not perpendicular. So I can't say perpendicular, we give it its own word because of the special case, okay? So the dot product is 0, it's orthogonal, not guaranteed to be perpendicular, okay? But if two vectors are perpendicular, they form a right angle, it's part of being orthogonal. Their dot product will also end up being 0. All right, so given a couple vectors here, we want to draw a sketch of the two vectors and see the angle and determine whether they are orthogonal or not. I don't even need to necessarily find the angle between these two vectors. I can just use my dot product, okay? So let's sketch them first. Let's sketch them. So I'd have 2, to the right 2, down 1. So I'll make this a little bigger. We'll go whoop. All right, so that'll be vector V. And then the other one, I'll use a lighter purple. We've got W, which will be to the right 3, up 6. Whoosh. There's W. Okay. So at first glance, it looks like it's plausible that these two have perhaps a right angle between them. Perhaps they are orthogonal. They're perpendicular, which would be orthogonal then. So let's find our dot product. Actually, we'll go with green. All right. So if I'm going to do my dot product of these two, I'll have 2 times 3 plus -1 times 6. And I'm left with 6 minus 6 now, which equals 0. So our dot product is 0. Boom. They are indeed orthogonal. Bingo. Now we could type this bad boy in to our calculator and also see that it's 90 degrees. Let's do that. Now, although we could probably see that if you have 0 inside the parentheses there divided by something, it's going to be 0. I typed it all in anyways. But what we get is the cosine inverse of 0. And when does cosine equal 0? It's at 90 degrees. So our answer would end up being 90. Shows that they're perpendicular. Bingo, bango, wonderful. Ooh, this one looks kind of fun. So it says, given vector V is 3i plus 2j, and W is 4i plus b, find b so that they are parallel and orthogonal. We were missing our lowercase j there. All right. So we want to find that value b so that they are parallel and so that they are orthogonal. Okay. Well, there's a couple ways to think about this. I personally like thinking about it from the slope component, right? Rise over run, Mr. Allen. Yes, rise over run. So if I look at my slope of vector v, that would be a rise of 2 and a run of 3. And I want to match that with my slope of w, which has a rise of b over a run of 4. So if I set 2/3 equal to b over 4, cross multiply and solve. Now you might be able to see it, I don't know. But if I cross multiply, I'd get 3b equals 8. This will be a weird way to write an 8, but I started writing a 2. Divide by 3, and I get b equals 8/3. There we go. So that will make them parallel. Same slope, parallel. I think that's the easiest way to think about it, especially if you actually know that slope is rise over run, unlike that mistake that I made. I'm so upset with myself. So upset. But I'm also thirsty for math and water. I've got water. Now let's do more math. All right. Orthogonal. All right. First one, method of slopes. So we know the slope of v is 2/3, which would mean that the perpendicular slope to v would be -3/2, right? Opposite reciprocal. Now I can take my slope of w and set it equal to that -3/2. So I'd have -3/2 is equal to, I already have b over 4, right? Already have that. So I'd get -12 is equal to 2b, so b is equal to -6. Boom. There's method 1. All right, with the slopes. Cool. So that would be to get them to be perpendicular to each other, which would then imply that they are orthogonal. Not the other way around, right? Orthogonal does not imply perpendicularity because of that zero vector situation. Now, the other option I could do is the dot product, right? And I'll switch colors for this one because green is getting monotonous. All right, so dot product would be that I would have 3 times 4 plus 2 times b, the unknown, and I want that dot product to be 0. So I can go through and just solve this equation. I'd have 12 plus 2b, and as you can probably already see, it's going to work out wonderfully. -12 divided by 2, and I get b equals -6. Awesome. Fantastic and wonderful. There we go. Uno más problema here. Just a little application. I wasn't going to leave you high and dry without some application. You want to know how this is applied, how meaningful this can be. Well, let's hop to it. All right. So we have a girl who's pulling a wagon with a force of 50 pounds. And as you know, if you pull a wagon, right, probably a Red Rider. I think that's the one. Then it's going to be at an angle of 30. There's going to be an angle to it. In this case, it's 30 degrees. It's not every angle. Every wagon angle is 30 degrees. How much work is done in moving the wagon 100 feet? That's it. Okay, moving it 100 feet. Sorry, I already gave the 30-degree thing. So, well, let's see here. I would have a vector, a force vector for the movement, or for that handle, right? The 50 pounds. So if I write up that vector here, I would have 50 times the cosine of 30 I hat plus 50 times the sine of 30 j hat. Okay? And let me go through and simplify a bit. Cosine of 30, that's going to be root 3 over 2, and then sine is 1/2. So let's work with those. 50 times root 3 over 2 I hat plus 50 times 1/2. I wrote an I there. That's a j hat. All right. Boom, boom. Awesome. And then we've got, 25 root 3 I hat. And then we have 25 j hat. Okay. So that's the force that's going on with moving that wagon. Now, work is defined as your force that you're applying, the dot product with direction, or multiplied by direction. Beautiful. So what's my direction vector going to be then, right? So I've got my force for how she's pulling the wagon. Now my direction, well, we're going 100 feet in the horizontal direction, right? So that's 100 in that I hat direction and 0 in that j hat direction. Cool? So what we're going to do is we're going to do the dot product of the force and the direction to get our work. Okay? So let's do that. So work is equal to force, dot product with direction. So I would have 25 root 3 I hat, right, times the 100 j hat. So 25 root 3 times 100 is... and then 0 times 25. So I'm just left with that for my work. Woo woo! Awesome. Fantastic. So there's an application of your dot product there to figure out your work, force, dot product with direction. You're going, obviously, it could be a little different. You're like pulling it uphill. This one was on a flat surface. So that's what we went with. All right. Hope you guys enjoyed it. I hope that background noise wasn't too bad. I do apologize if it was, but this is the only chance I can get this video done. Hope you guys have a wonderful day. America, freedom, rock and roll, Costco. Remember, yo row, you only round once. Riverdog J on the ground. Have a wonderful, wonderful day.